Like, this is a river, nice laminar flow of water. It's slower, right? The river water is slower toward the banks and speeds up and gets really fast toward the middle and then slows down toward the other bank. And, you know, something called the curl, you'd say, that thing shouldn't have it. But it does, right? That vector field has a curl. And, you know, there's a nice book, Div Grad Curl, and the guy who wrote it, this is one of these things, you read a whole book and there's one sentence and you go, wow, that makes sense, right? One of those little nice moments. And he said, no, you see, here's how you tell whether you've got a curl. Yeah, think of this as a flow of water. Now take a little paddle wheel, right? A little thing with just propeller things coming out on the side, and stick it in the current and see if it spins. And if it spins, there's a curl. And it's really obvious then that, yeah, there's going to be, if I stick it here, there's going to be more pressure on this side than on that side, and it's going to spin that way. And if I stick it here, it's going to spin that way. And if I stick it dead center, it's not going to spin at all. So immediately I know, yeah, there's a curl to that field, and it's zero in the middle, and it's one type of curl corresponding to clockwise and another type corresponding to counterclockwise along the sides. And the way I have it there, you'd even say, gee, it's probably a constant curl, right? Because this pressure differential looks constant there. And that's right? That's the right answer. So that was really cute. I liked that. But then I thought, wait a minute. If I'm a little two-dimensional guy, and I live in a little two-dimensional world that has two-dimensional rivers with two-dimensional water flowing through it, and the two-dimensional water happens to be flowing like that, I live in a world, a two-dimensional world with a curl, and I can't use my right hand to implement the right-hand rule, because I don't have anywhere for my thumb to stick out, right? I can't. So there's something incongruous about this particular piece of mathematics. There's something off. There's something a little weird about it. Right? Two-dimensional worlds should be able to have curls in them. Some people know there's different ways you can go. This is why I say I'm now inventing a new geometrical way of doing things where you would not be at all surprised that a two-dimensional world has curls in it, because they're obviously two-dimensional objects. But I won't get into that. So let's at least take the cross product out. I could go on and on about the problems of using vector calculus, but I want to get to a different point here. Let's take the cross product out and just write these now in a slightly more abstract form. So all we know about div is it's some function that takes in vector fields and kicks out scalar fields, and curl is some function that takes in vector fields and kicks out vector fields. And so, and if I no longer write the curl as nabla across anything, then you'd say, yeah, a two-dimensional world, they could have these equations without a problem, as long as I understand properly what a divergence and a curl is. So that's one thing that, you know, again, I'm just getting really down to the basics. So, I mean, maybe I should say, I think physics has gone is following the following wrong route, which is that people seem to think nature is a really, really, really fancy mathematician, right? You have to learn non-commutative geometry and topos theory and God knows what to get to the physics of the quantum gravity. I have exactly the opposite view. I think the world is kind of dumb. In fact, this whole mathematical thing I'm talking about, all you ever have to do is add and subtract. That's it. Nothing fancier than that. I don't think the world is such a fancy mathematician. I think there's maybe a problem if our mathematics is getting a whole lot fancier than the world is. There are some ontological moves you can make. Once you've put things in this standardized form, you can make some ontological moves. So for example, the way I had that written out, there was a current density. But what is a current supposed to be? An electric current is just supposed to be the motion of the charge density, rho. And we needed, I didn't have it on that list, but it's going to be defined in terms of the space and time structure. We're going to need a velocity vector v. I mean, you certainly know you need it in the Lorentz force law. So you say, maybe I shouldn't think of J as being a fundamental thing. It's a kind of derivative thing. And so I've got this equals sub ont. So that's ontological analysis, right? What J really is just rho in the direction of v, okay? At the speed of and in the direction of v, where v is the velocity vector field that's associated with the charge density. Now, I could go on for yet another lecture about how weird it is for there to be velocities associated with continuous densities, because particles, you know what their velocities are, right? Because they've got nice world lines that have nice tangents. But densities aren't like that. They're mush, right? What is the velocity of a density? I mean, what determines its velocity? I would like, it's much easier if at the end of the day, at the bottom, you have particles, point particles moving, and when you talk about rho, that's always at a macroscopic scale, and you're averaging, right? But let me leave that problem apart. We've got enough to deal with. The other thing is, my own view is that the fundamental laws of nature, well, my own view is that there should only be one. Ultimately, there is one fundamental law of nature, and that it is fundamentally a dynamical law which tells you how things evolve in time. And you might notice that of the four Maxwell equations, two of them don't mention time. One of them is this div E equals rho. That's not a dynamical law. You could also take that as a kind of ontological reduction. You could say, look, maybe charge just is the divergence of the electric field. If I'm already committed to an electric field, and I understand what it is for a field to have a divergence, maybe I should think of this not as it were, an equation that connects two fundamentally different things by law, but as an equation that's telling me what one of the sides is in terms of the other, right? And if I have an electric field, it's already got a divergence. It's just there. It is what it is. So let me just say that's what rho means, right? That's what rho is. So I move that out of, so I'm talking about ontological moves. I move that equation out of the nomology, it's no longer a law, into, all right, I'll go more quickly, into another category. Similarly, for a div B equals 0, you could say, look, that's just a mathematical way of saying there are no magnetic monopoles. It's not a dynamical law. You can regard it as a mathematical expression either of the physical impossibility of monopoles and absorb it into the conventions, or you can accept it as a contingent fact. So there are lots of ways to do this. Now what I want to do is talk quickly what everybody knows about the scalar and vector potentials. In classical theory, they're regarded as mathematical pseudo-objects. The existence of the scalar and vector potentials, A and phi, follows by purely mathematical considerations for any E and B, so long as div B equals 0, and we have that in the nomology, so we're guaranteed of that, and so long as the curl of A plus E plus dA dt equals 0, and we can make sure that that's right. And so we know that as long as we have E and B that satisfy the equations, A and phi will exist. But we also know that not only will one such pair of A and phi exist, but if one does, then there are an infinite number of other ones that do exactly the same job in reproducing E and B, right? And we can, so if you give me an A and phi that work, if I add the gradient of any arbitrary scalar field psi, and I guess that shouldn't be bolded, sorry, and that make this transformation, I'll get another A prime and phi prime that do the same job. So there are an infinite number of these A phi pairs, and we say that they're all related by a gauge transformation, and that's merely a gauge degree of freedom. It doesn't represent a physical degree of freedom in the system. So from all this, we can get classical electromagnetic theory version 1 in various types. So here is a canonical form of a commentary here's what the theory's called, here's what the physical ontology is, here's what the mathematical representation is. The purely mathematical facts tell you about the existence of the A and phi. I've left out the talk about space and time, but we have enough on our plate. There are the fundamental laws, including the Lorentz force law and Newton's law, and we have the scalar and vector potentials as mathematical pseudo-entities. That's a way to understand that mathematical formalism. But I can make these moves, right? I can, as I say, I can take J out of the fundamental ontology and make it a derived thing. So J equals rho v gets moved over into that column. I drop it out of the nomology. I now have one less law. I can make the other move, which is to say div b equals 0 is just a way of saying there are no magnetic monopoles. That drops out of the nomology, right? I'm told that that's what that equation expresses, and now I have one less law. And I can do both of those things and get my nomology down to just from the 4 original Maxwell laws down to 2, and I still have Newton's laws there. So you see what I'm doing, right? So each of these, in my view, are different theories, different physical theories using the same mathematical apparatus with different commentaries.